In our last video, we will see some useful applications of Josephson junctions in quantum technologies. We will start with the use of superconducting quantum interference devices to detect tiny magnetic signals with high sensitivity. Qubits are extremely sensitive since they can transduce small flux changes of the order of the flux quantum or less into measurable electric signals. This allows detecting tiny variations of the magnetization of nanoparticles, magnetic textures, or current states. This can be done by simply measuring the critical current of the qubit, but this comes with the drawback of being a stochastic process, depending on temperature and also on the probability of quantum tunneling. On the other hand, biasing a non-hysteretic qubit with a current close to the total critical current will produce a direct, easy-to-measure voltage signal, periodic on the flux quantum. These qubits can be operated in the linear response regime or in a closed feedback loop that allows linearization of the flux to voltage periodic response. This property also allows operating the qubit as a floating element, enabling the sensitive detection of small magnetic signals. The so-called RF qubit is inductively connected to a radiofrequency tank resonator, composed of a superconducting inductor and capacitor in parallel. The resonance frequency of the tank circuit will be given by 1 over the square root of the capacitance and the effective inductance, which also depends on the inductance of the floating qubit, that depends therefore periodically on the applied flux. Alternatively, the qubit can be integrated into the LC resonator itself, which allows detecting small variations of the qubit inductance in a reflectometry configuration. In this way, the qubit behaves as a sensitive flux-to-phase detector. We will next learn about the implementation of superconducting qubits. But first of all, what is a qubit? A qubit is nothing but a two-level system that serves as computational basis to perform quantum operations. This can be built from a true two-level system like a spin-1/2 half, or a system characterized by several energy levels with distinguishable transitions, like a larger spin with anisotropy. Alternatively, we can also use superconducting circuit elements to build an oscillator with quantized energy levels. The problem of this approach is that it will result in a harmonic oscillator with equally spaced energy levels. Fortunately, thanks to the Josephson element, it is possible to break this linearity. Do you remember about the resistively and capacitively shunted junction model? It allows us to understand the behavior of junctions in the phase regime, for which the Josephson energy is larger than the charging energy. The latter means that Cooper pairs can easily fluctuate between both superconducting electrodes, while minimization of the energy is achieved when the phase is fixed and well-defined at a minimum of the washboard potential. At zero bias current, energy minima correspond to phase equal to 0 or integer multiples of 2 pi. Under these circumstances, the particle stays within the potential well and can oscillate at the plasma frequency. Since the plasma energy is much smaller than the height of the potential well, a classical description of the particle oscillations is well justified. However, it is also possible to exploit the quantum and anharmonic nature of Josephson junctions by biasing them with a current very close to I sub 0. In this way, the height of the potential well can be reduced, becoming comparable to the separation between the quantized oscillation levels of the particle. For instance, using conventional niobium aluminum oxide junctions polarized at 99% of its critical current, you can obtain level separation of tens of gigahertz with 3 up to 5 levels within the potential well. By doing so, you will have obtained your first superconducting qubit, the charged qubit. Another important example of phase qubit is the flux qubit, based on an RF qubit, to which more junctions are added to increase the inductance of the loop. Combining the Josephson periodic potential with the quadratic dependence of the inductance on the circulating current, two potential minima appear. that correspond to clockwise and counterclockwise circulating currents. Quantum mechanically, the degeneracy is broken and energy differences appear between the symmetric and the anti-symmetric combination of clockwise and counterclockwise currents, which set the operational basis of the qubit. At this point, the energy depends little on the external flux, making it quite insensitive to flux noise and receiving the name of sweet point. Also interesting for building qubits is operating junctions in the charge regime. Here, the capacitance of the junction is so small that the charging energy dominates over the Josephson energy. The phase of this junction has the largest uncertainty, whereas the number of Cooper pairs is well defined. Moreover, if the resistance of the junction is larger than the resistance quantum, the junction will operate in the Coulomb blockade regime, and Cooper pairs will tunnel one by one. This idea forms the basis of charged qubits or Cooper pair boxes. These qubits consist of a small superconducting island connected by a Josephson junction to a superconducting reservoir. The small size of this island means that the introduction or extraction of individual Cooper pairs results in appreciable energy changes. Additionally, the junction is voltage biased through a capacitor at the degeneracy or sweet point. Thanks to the Josephson coupling, the classical degeneracy of the state with 0 and 1 Cooper pair is broken. A gap is thus opened between states corresponding to the symmetric and anti-symmetric combinations that represent the states of the charged qubit. An improved version of the charged qubit is the transmission line shunted plasma oscillation qubit, or transmon. This is a charged qubit in which the Josephson energy is greater than the charging energy, which can be achieved by shunting the junction with a large capacitor. By doing so, the sensitivity of the qubit to charge fluctuations is strongly reduced, although at the cost of having close to harmonic energy transitions. Transmons are currently one of the dominating qubit technologies in superconducting quantum computers. However, in the last years, a different version of the transmon is gaining ground. Substituting the capacitor by a superinductor, the fluxonium guarantees protection against both charge and flux noise, while retaining large anharmonicity. Josephson junctions are also the basis for the best amplifiers in terms of noise that we have to date, parametric amplifiers. To understand the working principle of a parametric amplifier, think of a child on a swing. By moving the body back and forth, the kid manages to change the center of mass of the pendulum. This effectively modulates the characteristic frequency of the swing, just at double its original resonant frequency. This allows the kid to amplify the swing amplitude. To see this, take the equation of an unriven harmonic oscillator with characteristic frequency omega0. Then add a term that modulates the resonance frequency of the system by means of a pump signal at exactly 2 times omega0. If your harmonic oscillator was initially moving, you will see how this equation can be rewritten as that of a harmonic oscillator driven at precisely omega0. The same phenomenon is well known in optics, thanks to the use of non-centrosymmetric crystals, for which the refractive index can be modulated by an electric field. In the so-called optical parametric amplifier, one weak wave is passed through a non-centrosymmetric crystal together with a pump wave at double frequency. A cavity is typically used to increase the light-matter interaction. This is called three-wave mixing and yields 2 photons of the pump wave being transferred to the signal wave, amplifying it. The heart of Josephson parametric amplifiers is an LC resonator plus the ability to modulate one circuit parameter, the inductance. It must be noticed that one possibility is to exploit the current-dependent kinetic inductance of small cross-section superconducting materials by using a circulating supercurrent. However, along this tutorial, we will concentrate in inductance tuning by means of the Josephson effect. Three-wave mixing requires non-symmetric dependence of the inductance on the current, but simple Josephson junctions are quite symmetric. To solve this, you can think of a flux bias squid loop. Bias at 1/4 of the flux quantum, the inductance is indeed linear function of the applied flux, and therefore a linear function of the circulating current. The setup typically consists of an LC resonator, in which the inductance is replaced by a DC squid that can be flux biased at a convenient operation point, while introducing the pumping wave in the form of a flux modulation at double the characteristic frequency of the resonator. Operated in reflectometry, this system allows amplifying signals while theoretically adding no noise. This has to be done with care, since, just as the case of the kid in the swing, if you pump out of phase, the system will not amplify, but de-amplify. The phase difference between the resonator and the pump is therefore of enormous relevance, and amplification is said to be phase sensitive. If the pump is not precisely tuned at 2 times omega-0, amplification is still possible. This is called a non-degenerate amplification, and will yield the production of a second wave called the Idler. The gain of this amplifier will not be optimum, and the theoretical minimum added noise corresponds to half a photon. But phase matching will be less of an issue, and operation will be simpler. We have just seen that we can implement parametric amplification by means of a conventional harmonic oscillator, as long as we can find a way to modulate its resonance frequency. This is to say, the parametric amplifier is not driven by the action of a driving force, but by periodically varying one parameter of the system. Now, there is an alternative way of implementing parametric amplification. For this purpose, we will need a non-linear harmonic oscillator. This can be mathematically achieved by adding a quadratic term, which is well described by the Duffin equations. We drive the system as usual, by means of an external force oscillating at the characteristic frequency. At low powers, nothing special happens. However, as you increase the amplitude of the driving, you will observe how the response of the nonlinear oscillator becomes distorted. The resonance frequency is shifted an amount proportional to the oscillation amplitude squared. In this way, we have found an alternative way to modify the resonance frequency of the oscillator. This is not achieved by modulating one parameter of the system, but by exploiting the nonlinearity of the circuit. This effect arises also in optics, in centrosymmetric crystals, for which the refractive index depends on the light intensity, becoming nonlinear. However, these kinds of three-order effects are quite weak. Practical amplification process is only achieved when signal and driving waves interact over long distances compared to the wavelengths involved, as in optical fibers. This is called four-wave mixing, and also yields the amplification of the signal tone by transferring 2 pump photons to the signal and Idler waves respectively. Now, remember that Josephson junctions are strongly nonlinear objects. This can be seen by expanding the current-phase relationship, yielding the so-called Kerr term, in analogy to optics, which is cubic in phase. As in optics, the latter allows modulating the inductance of the junction by the current squared. Four-wave mixing can be implemented in a resonator configuration, as we have just seen. However, it can be harder to separate the output amplified signal from the pump tone, since they come at similar frequencies. Even worse, three-order Kerr effects are quite weak, requiring the use of high pump powers. The devices we have seen are based on the use of cavities. Cavities, however, suffer from severe restrictions in terms of bandwidth. There is an alternative way of increasing the interaction between light and matter, similarly to optical fibers. Josephson traveling wave amplifiers are designed as microwave transmission lines made of several Josephson elements. In this way, propagating microwaves can interact and mix, yielding parametric amplification free of bandwidth limitations. Design becomes complicated as traveling wave amplifiers must include several elements to avoid phase mismatch. These devices usually perform in the 4-wave mixing regime, although much efforts are devoted to the design of more efficient Josephson traveling 3-wave amplifiers. Building a fault-tolerant quantum computer is tough, but this is not only due to the cryogenic circuitry. Also, the room temperature hardware poses many challenges. It is expected that a single logical qubit will be composed of hundreds of physical qubits, each requiring multiple radio frequency lines and room temperature electronics. Scaling up to million physical qubits will not be possible unless other approaches are developed for qubit control and readout. This circuitry should ideally be based on superconductors to reduce the heat load and power consumption. This would also allow operation at cryogenic temperatures, close to the quantum processor, to minimize the wiring. One possible alternative fulfilling these requirements is rapid single-flux quantum technology. This is a superconducting family of logic that was originally proposed in the 80s to substitute CMOS technology. In RSFQ, logical bits corresponds to the presence or absence of a voltage pulse within a clocking period. One clever way of producing identical short-time voltage pulses is to use a Josephson junction. Remember again the resistively and capacitively shunted junction model that describes the dynamics of the phase as that of a particle in a washboard potential that is tilted by the action of a bias current. Imagine a shunted non-hysteretic junction biased at a current close to its critical current. An incoming electric pulse produces a brief tilting of the potential, yielding a phase leap equal to 2 pi. Using the second Josephson relation, such phase jump translates into a voltage pulse with quantized area equal to the flux quantum, that is a tiny quantity of just 2 mV per picosecond in typical Nairobi shunted junctions. RSFQ voltage pulses can be transmitted through superconducting transmission lines, but due to their extremely narrow time width, they contain multiple frequencies that might yield dispersion of the pulse during transmission. For that reason, pulses are usually propagated using Josephson transmission lines. These are formed by a series of shunted non-hysteretic Josephson junctions, biased close to their critical currents. If a voltage pulse enters the line, it triggers a 2 pi phase leap in the first junction, yielding the emission of another single flux quantum voltage pulse towards the second junction. As voltage pulses are transmitted towards the right part of the circuit, successive Josephson junctions reset into their supercurrent state. Power dissipation can be reduced even further by avoiding the use of bias resistors. In the so-called efficient rapid single flux quantum, current sources are implemented by using an additional voltage bias Josephson junction, with critical current close to the desired bias current. In a similar way, you can think of more complex circuits that will allow you to perform directional transmission of voltage pulses, splitting or fan-out, and even storage and retrieval of single flux quanta using squid loops. It turns out that voltage pulses can be used to induce qubit rotations in superconducting qubits such as transmons. Imagine you connect a generator of voltage pulses to your qubit by means of a coupling capacitor. One single voltage pulse produces a discrete rotation of the qubit state about the y-axis. After that, the Bloch vector will precede freely about the z-axis at the qubit frequency. In this way, rotations to arbitrary angles around the y-axis will be possible by sending trains of pulses, as long as the time between pulses is carefully chosen to match the qubit frequency. Using a pulse interval that is slightly mismatched from the oscillation period, the state vector will drift away from the xz plane, enabling arbitrary qubit control. Similarly, pulse trains with tuned interpulse period can be used to prove the resonant frequency of a superconducting cavity, enabling also quantum non-demolition readout of qubit states. Efficient rapid single-flux quantum generators are ideally suited for these goals, being low dissipative, compact, and avoiding the use of room temperature microwave electronics. All applications of the Josephson effect that we have reviewed along these videos are the subject of intense research. There is still much room for improvement and many problems to solve, but the Josephson effect will probably play a central role in future quantum technologies in one way or another.